We continue with our discussion of proceeding from observations of motion to the determination of forces using Newton's second law. Earlier we considered equilibrium cases, both static equilibrium and dynamic equilibrium. We now turn to situations where the velocity is changing. We know from Newton's second law that when the velocity changes, the net interactions are non-zero. We can still progress from observations of the system's motion to determining unknown interactions via the same key steps we applied for the equilibrium case. However, how to apply these steps for cases with non-zero F net requires additional discussion. In particular, we need to discuss the thinking that's required to implement the key step of proceeding from observations to some understanding of F net. That's what we'll begin with today. Let's start by introducing a more systematic way of classifying changes to an object's velocity. Recall that when we watch something move, we know to look for changes in the velocity as the key signature that the total interactions are non-zero. Moreover, we know that changes to the velocity can arise by changes to the velocity's magnitude, by changes to the velocity's direction, or by both the magnitude and direction changing at the same time. Now we know that the change in velocity, which we represent here graphically using arrows, captures all those changes. However, if we dig a little deeper here, we can come up with a helpful way to describe such changes using a natural choice of coordinate axes. The orientation of the first axis in this coordinate system is determined by the motion of the object before the change. We align one axis parallel to the initial velocity. We will label this axis with the parallel symbol. With this axis in mind, we can see that a projection of the vector delta v may lie along this axis. Let's label that projection delta v parallel. Now if we subtract delta v parallel from delta v, we end up with the leftover part of delta v, which is perpendicular to the initial direction of the motion v initial. We use the perpendicular symbol to label this, delta v perpendicular. We'll discuss in a future lecture a geometric way to think about this perpendicular direction. For now, let's focus on the idea that, in general, the total velocity change can be written as the sum of the change along the direction of motion, delta v parallel, plus the change along a direction perpendicular to the motion, delta v perpendicular. Before we say more about motion changes along these parallel and perpendicular directions, we're going to point out that we can also use the physical quantity of momentum instead of velocity to describe motion and motion changes. For most problems we'll consider in this course, we can think of the momentum as a positive scalar, the mass, times the velocity. So a momentum quantity always points in the same direction as the corresponding velocity quantity. In particular, here delta p points in the same direction as delta v. And moreover, delta p can be decomposed into the sum of delta p parallel and delta p perpendicular, each of which point in the same directions as, respectively, delta v parallel and delta v perpendicular. For the next few lectures, we'll be making more use of describing motion and motion changes using momentum, because we'll see there will be a few advantages to this, including making our discussion more consistent with the textbook. Let's now provide some physical motivation for thinking about changes in momentum and changes in velocity along these parallel and perpendicular directions. First, let's consider the case where delta p and delta v are only changing due to changes along the parallel direction. What kind of motion change would we see? Let's discuss this in terms of the momentum. The same language would apply for describing these motion changes in terms of the velocity. A major feature of this kind of change is that it always occurs along a straight line, along the same line that the object is originally moving. So here's one way that can happen. The object's final momentum is greater in magnitude than the initial momentum. So delta p looks like this, only changing along the parallel direction, a change that corresponds to the object speeding up. Here's another way. The object's final momentum is smaller in magnitude than its initial momentum. So delta p looks like this, again changing along the parallel axis. This is a change that corresponds to the object slowing down. So here's a key point. The magnitude of the momentum can change only if delta p parallel is non-zero. Now there's a third kind of motion change along a line that can happen with delta p parallel non-zero. It's a combination of slowing down and speeding up that leads to the object reversing direction. One concrete example of this is the motion of a mass on a spring. Think of the object moving downward initially, then later moving upward. In between, the object comes to rest momentarily. Before this moment of rest, the object is slowing down. After that moment, it's speeding up. We can calculate delta p, and we can see this is a non-zero delta p along the parallel direction that leads to a special kind of direction change, a reversal of the direction of motion. Now let's discuss what happens when the momentum and the velocity change only in the perpendicular direction. In this case, the path of the object, the trajectory, exhibits a curvy appearance. In particular, the object moves at constant speed in a circular path. This is so because if the changes are always perpendicular to the direction of motion, the length of the momentum and velocity vectors can't change. But the velocity and momentum vectors themselves do change because they change direction. So let's conclude this lecture by summarizing. It's useful to decompose changes in the momentum, or equivalently, changes in the velocity, along a direction parallel to the object's original motion and a direction perpendicular to that. The object can speed up or slow down only if there are changes along the parallel direction. That is, delta p or delta v are non-zero along the parallel direction. The object's path can curve only if there are changes along the perpendicular direction. That is, delta p or equivalently delta v are non-zero along the perpendicular direction. Of course, parallel and perpendicular changes can be non-zero both at the same time, in which case we would have a combination of speeding up or slowing down and curving motion. Next time, we'll provide a more formal way to describe this by examining the ratio, the change in momentum over the change in time.